And let's do another insurance application. This time, instead of a deductible, let's say the policy has a maximum payment. So X is once again the loss of the person, like in a car accident. Let's, like in the homework problem, assume this is exponential with mean of 1,000. Exponential with mean equals 1,000. Mean is same thing as the beta for an exponential distribution. Its PDF is 1 over beta, e to the negative x over beta. This time, y was still the insurance payment, but instead of there being a deductible, there's a maximum payment. The insurance wants to cover themselves in case you have $1 million loss and not pay $1 million. Now, of course, a car is not going to be worth $1 million unless it's some crazy collectible. But there's no deductible. Let's say they pay X if, oh, for example, X is less than 2,000. But they never pay more than 2,000. So once again, y is a piecewise function of x. With deductibles, it was 0 in the first spot and x minus the deductible in the second spot. With a maximum payment, a cap, it's called capped insurance. It's x in the first spot, whatever the loss is, as long as the loss is less than the cap, and then it equals the cap or the maximum if x is greater than or equal to the maximum. I could call this function h of capital X if I like, or I guess I should call it capital H to be consistent. And certainly to find the mean of y, it's actually easier than thinking about the CDF and PDF. You can use the generalized expected value formula for a function of the original random variable in the general case. That's going to be this, where this is the PDF of X here, not Y. And for our situation, when X is exponential, it's going to be an integral from 0 to infinity, you might say, but also because h of x takes on a constant value of 2,000, once x reaches 2,000, careful, we aren't going to get one integral, though. We are going to get two integrals. The integral from 0 to 2,000 of x times the PDF of x. PDF of x exponential with mean 1,000 is going to be 0.001 e to the negative 0.001 x. But then I have to add the integral from 2,000 to infinity of 2,000 times the PDF. 2,000 times 0.001, I'm running out of space here, e to the negative 0.001 x. Right? I am integrating h of x times f, but I can split that into two pieces because the h function is piecewise. This one you'd have to do integration by parts to do it by hand. This one you wouldn't. For the sake of time, let's just have Mathematica do this. Think about it intuitively. The mean of x itself is 2,000. The integral from 0 to infinity oh no, 1,000, sorry. 0.001 times e to the negative 0.001x. Okay, this is just the PDF, so this integral is going to be 1. Oops, forgot my negative sign. Integral of x times that is going to be the mean, 1,000. But our mean for y, this capped insurance, is the integral from 0 to 2,000 plus the integral from 2,000 to infinity, where this is an x and this is a 2,000. It's got to be less than 2,000. That. The mean of x, it's got to even be less than 1,000. The mean of x is 1,000. The mean of y is less than 1,000. Because you're not going to have, x could have very high outliers. Y is not going to have very high outliers. It never gets bigger than 2,000. So it should be intuitive that its mean is smaller. And we can simulate. I won't take the time to do that. Let's instead find the CDF of y and wonder whether whether it might be discontinuous again. You don't have to find the CDF and the PDF for the mean. That's nice. But it's interesting to still find the CDF and the PDF. The PDF, it's going to be a mixed random variable. So the PDF is not something you can easily describe. But the CDF is definitely possible to describe. CDF of y. Think about it intuitively here. Well, it's the probability that capital Y is less than or equal to a given little y. Once little y gets to 2,000 or above, the probability is 1. X could be bigger than 2,000, and the probability that x is, for example, less than 3,000 is not 1. Close to 1, but not equal to 1. But y never can get bigger than 2,000. So if I put a 2,000 there or anything bigger, it's a guarantee. 1 is the probability. Like the harder part is when y is less than 2,000. But this is actually easier than the deductible, because y equals x if x is less than 2,000. Capital Y can be replaced by x if the number to the right, now I'm calling y, is less than 2,000. With a deductible, it was in the case where x was bigger than the deductible, you had to replace y with x minus the deductible, and you had to add the deductible to both sides of the inequality, and it was a little trickier. This is a little easier. Y, capital Y equals capital X if this number is less than 2,000. And so then you just need the CDF of capital X and plug in Y instead of little x. And let me reorder these. And that'll be 1 minus e to the negative 0.001 times little y. It's a piecewise function. Is it continuous? No, it does have a discontinuity. Well, let me also add 0 if y is negative. Sorry, this is not very clean homework. I was assigning this to myself as homework. Where's the discontinuity? Is it 0? No, the discontinuity is at 2,000 this time. It's at 0 for the deductible insurance. It's at the cap for capped insurance. Graph of capital F sub capital Y. Can be 0 over here. This does have a limit of 0 as y goes to 0, because e to the 0 is 1. 1 minus 1 is 0. But as y approaches 2,000 from the left, this does not approach 1. Does it approach? Replace y with 2,000. 001 times 2,000. E to the negative 2. Not 0. 1 minus that is not 1. It's about 0.865. And technically, I should be careful about where's the open circle and where's the closed circle here. At y equals 2,000, we jump up to a probability 1. So the closed circle should be up here. And there should be an open circle there. That's what the graph of the CDF looked like. The PDF is going to look like an exponential decay, except then jump down to 0 when you get to 2,000. Technically 0 over here as well. What is its value at 2,000? Not 20,000. What is its value at 2,000? Well, technically speaking, you should really say it's undefined, right? This is not differentiable at 2,000. However, that can be problematic in terms of the more general theory, actually. In effect, you end up saying it's infinite at 2,000. In a sense, there's an infinite jump there, infinite slope, you might say. But it's not any old infinity. It's an infinity that makes the PDF integrate to 1 when you integrate it from 0 to 2,000. If you only integrate this part from 0 to 2,000, you're actually not going to get 1. You'll get 0.865. In effect, the value of the PDF has to be infinite at 2,000 in such a way that when you integrate to including past 2,000, the integral is 1, as it has to be for a valid PDF. And to get into what this means and how you do it, it's again beyond the scope of this course. Theory of distributions, generalized functions, Dirac delta function. Most of you never heard of that probably. Okay, but you actually can make it rigorous, but we're not. Some people don't, that's supposed to be an infinity, by the way. Some people don't say it equals infinity there. Some people put a finite value. They put 1 minus 0.865 in this case. Wherever that is on here, I don't know where it is. But that is sort of a misrepresentation of what the PDF in this kind of context means. This part you'd integrate to find probabilities, but the part over here you'd plug in a value instead of integrating. So it all gets confusing, but don't worry about it. I'm not going to test you on the PDF of this. I could have tested you on the CDF. Okay, but again, to find expected values, you can always use the PDF of X, so it's easier. You don't have to find the PDF of Y. All right, have a good day.